It's almost magical how AI can now conjure images from just a simple text description.
Right.
But if you've ever tried to get really specific,
Oh, yeah.
say you want a fluffy Persian cat wearing a tiny top hat sitting on like a particular kind of park bench, you quickly realize that controlling the AI with that level of detail, especially about specific subjects, well, it's surprisingly hard.
That's a crucial point. Um, the real frontier now in AI image generation isn't just about generating any plausible image. It's about getting that fine-grained, in-context control over particular subjects,
Right.
making sure the AI understands and, consistently reproduces specific features across different generations. That's been a significant challenge for the field. Yeah.
Well, we've got some potentially really interesting work to unpack today. We're taking a deep dive into the new approach called UNO, that's UNO, developed by the ByteDance Intelligent Creation team.
Oh, ByteDance. Okay.
Yeah, and their research, it's detailed in the paper, Less to More Generalization, Unlocking More Controllability by In-Context Generation. And it seems to directly tackle this issue of getting highly controllable, subject-driven image generation.
And it's particularly interesting, I think, from an academic standpoint, is the core problem UNO is trying to solve. Basically, how hard it is to scale up subject-specific generation, especially when you're dealing with, say, multiple subjects, or you need lots of different variations of just one subject.
Hmm.
This limitation often comes down to just not having enough training data that covers all those possibilities, those variations.
Okay, so before we jump into UNO itself, maybe let's set the stage a bit. What were the main academic ways people were trying to solve this subject-driven generation problem before? And, what were their big limitations from a research angle?
Okay, yeah. Broadly speaking, you can kind of divide the existing research into two main streams. First, you've got methods based on few data fine-tuning.
Like Miriam Booth.
Exactly. Think Dream Booth, textual inversion, and maybe the more recent LoRi stuff. These techniques use just a small number of images, often provided by the user, to adapt a big pre-trained model so it can accurately show a specific subject.
So the academic plus there is getting really good likeness, high fidelity, even with just a little bit of data.
Precisely. The key contribution is how they efficiently tweak the model's internal representation, its latent space, to capture the details of that new subject using only a few examples. But the academic drawback is the cost, computationally speaking, and how slow it is at inference time.
Because you have to fine-tune for every single new subject.
Exactly. You need to run that fine-tuning process again and again, and that fundamentally limits how scalable these methods are, or if you can use them in real time, especially if you need to generate lots of different subjects quickly.
Right, so academically neat for being data efficient, but they hit practical walls with scaling. What's the other main research path?
So the second major direction involves training on huge amounts of data. Methods like IP adapter or blind diffusion, they take the opposite approach. They train on these massive, diverse data sets of images paired with text descriptions.
Ah, okay.
And this lets them do direct, real-time customization without needing that per-subject fine-tuning step.
So the academic draw here is scalability and speed at inference time.
Exactly, because they learn this kind of joint space where visual and text features mix, learned from this huge amount of data. Theoretically, these models can generalize better to new subjects without needing specific fine-tuning.
But there's always a but.
Well, yeah, the inherent academic challenge is the data itself. Even these massive data sets, they might still lack enough examples of very specific or, rare subjects and all their little variations.
Hmm.
So this can lead to a trade-off, right, between how much the generated image looks like the reference subject versus how well it follows the text prompt. Plus, the model's abilities are ultimately kind of capped by what it learned from that initial big data set.
Okay, so both main research streams have these built-in limitations, either scaling issues or data coverage problems. So here's where it gets academically interesting. How does UNO, conceptually and architecturally, try to get around these fundamental challenges?
Right. The central academic novelty, the really new idea in this work, is introducing what they call a model data coevolution paradigm.
Model data coevolution.
Yeah, it's a conceptually pretty significant shift from how things were done. They actually draw inspiration from how large language models seem to improve themselves by generating synthetic data.
Okay, model data coevolution. Break that down for us. From an academic view, what's the core theoretical idea?
So the core idea is basically setting up a positive feedback loop between how good the model is and how good the data is. You start with maybe less controllable generative bodies, and you use them strategically to create better training data.
So our model makes its own homeworks, essentially.
Kind of. And this improved synthetic data is then used to train the next generation of models, making them more controllable. Then these better models can, in turn, generate even more refined training data.
Ah, I see.
So you get this continuous cycle where both the model's abilities and the richness of the training data improve together. It's a move away from just relying on static, often human-labeled datasets towards something more dynamic, like a self-improving training process.
That is a theoretically fascinating concept, the AI kind of bootstrapping its own learning. Is there a key quote or sentence from the paper that really nails this innovative idea from that academic perspective?
Yeah, there is. The authors stated pretty clearly, this study proposes that achieving stable and scalable customized generation necessitates an analogous model data coevolution paradigm, where less controllable preceding customized models systematically synthesize better customization data for successive more controllable variants.
Okay, wow.
And the academic significance there is really spelling out this need for a dynamic back and forth between the model and the data to get past the limits of static datasets, especially for robust, scalable custom image generation.
Okay, so this coevolution idea is the big theoretical contribution. Now, how does the actual architecture they built, make this happen? What are the key architectural innovations that enable this cycle?
Right, so is the concrete way they implemented this coevolution principle. It's built on top of diffusion transformers, or DAT.
DAT, okay.
Yeah, and DATs are known for being architecturally scalable and pretty good at handling multiple conditions like text and images during generation. UNO's architecture is specifically designed to really unlock and use those multi-conditional abilities within the DAT framework.
And to get this better controllability, they introduce some specific technical tricks at the architecture level, right?
Exactly. UNO brings in two main technical contributions to make this coevolution happen. First, a progressive cross-modal alignment strategy, and second, a novel position embedding thing they call universal rotary position embedding, or UNOP.
All right, let's take the first one, progressive cross-modal alignment. Academically speaking, what's the thinking behind it and what's technically new about this stage training?
So the thinking is that it's just really hard to learn how to handle both text instructions and multiple visual inputs all at the same time effectively.
Okay.
The technical novelty is breaking the training into stages. In stage 1, they take a standard text-to-image model, a T2I model, and fine-tune it to become a single subject-to-image, or S2I, model. And crucially, they use synthetic data of single subjects for this, data generated by an earlier, less refined model.
Ah, the coevolution starting right there.
Exactly. The input at this stage academically looks something like Z1 equals concatenate S, CZTES, RF1, where C is the text, CST is the noisy image representation, and EIF1 is the embedded feature of one reference image.
So the model first learns to connect a single visual subject to the text. Then what's the progression to stage 2 and what's the added academic value?
So in the next stage, this pre-trained S2I model gets more training, but this time using synthetic data, it features multiple subjects.
Okay, ramping up the complexity.
Right. This lets the model learn how to handle more complex scenes involving several reference images. The input now becomes something like Z2 equals concatenate us, where you have embeddings for multiple reference images. They used equals 2 in their experiments.
And the academic value.
The academic value is showing this progressive learning strategy really helps stabilize the training when you start adding more complex conditions like multiple visual inputs. It avoids the kind of instability you often get if you try to train everything end-to-end from the start.
That staged approach sounds pretty critical for stable learning. Okay, let's dig into the second key architectural piece, this universal rotary position embedding, UNOP. What specific academic problem is it solving, and how is its mechanism a novel solution?
So UNOP is specifically designed to fix this problem they call attribute confusion, which can happen when you scale up the number of visual subject controls.
Attribute confusion, meaning the model gets mixed up about which details belong to which subject.
Sort of, yeah. Or academically, it means the model might rely too heavily on just the spatial layout of the reference images it sees and potentially ignore the layout or relationship info that's actually in the text prompt.
Ah, so the challenge is making sure the model understands which subject is which, based on the text, not just where they appeared in the input images.
Precisely. And UNOP offers a novel fix by basically strategically messing with the positional information of the reference image tokens inside the transformer. Instead of just using their original spatial coordinates, UNOP offsets these positions relative to the dimensions of the main noisy image tokens. There's a diagram, figure 4 of the paper, that shows it. Mathematically, it's like I plus W NA1, J plus H NA1.
Okay, from an academic angle, what's the theory behind why this specific kind of position manipulation works? Why offset them like that?
The theory is that it encourages the model to pay more attention to the overall layout and the semantic relationships described in the text. By offsetting the reference image positions, UNOP makes it less likely the model will just copy the spatial arrangement it saw in the inputs.
I see.
It forces the model to more actively use the text instructions to figure out the right spatial layout and who gets which attributes in the final image. And this leads to better subject accuracy and sticking closer to the text prompt.
Okay, so these architectural changes are key, but the whole model data coevolution thing really puts the spotlight back on the data itself. Tell us about their systematic synthetic data curation framework. What's academically novel about how they make the data for this coevolution?
Yeah, that synthetic data framework is absolutely central to making the coevolution paradigm actually work. Its academic novelty is really in its progressive, multi-stage way of generating high-quality paired training data. It uses the DAT's capabilities to create data that gets progressively more complex, starting with single subjects, then moving to multi-subject scenes.
And they mentioned high resolution too.
Yes, another important point. The framework produces high-resolution outputs, 1024 by 1024, 1024 by 768, 768 by 1024. This is a pretty significant step up in the quality and diversity of synthetic training data compared to earlier work like immediate control.
High res is great, but how do they make sure the data is actually good? Like, what's the academic rigor in their quality control?
Good question. They use a pretty rigorous multi-stage filtering process. First, they use DynOff2, which is a strong, self-supervised vision model for an initial filter based on whether the subject in the generated image looks consistent with the reference image.
So a basic semantic check.
Right, just making sure it's roughly the same thing.
But Dunoff 2 is about visual similarity. They go deeper for quality assessment, don't they?
They do. For a more detailed check, they bring in a vision language model, a VLM, and use it with chain of thought prompting.
Chain of thought, like asking the VLM to explain its reasoning.
Exactly. Academically, this is significant because it gives a more interpretable and detailed quality score. They prompt the VLM to explicitly think about different aspects. Does the subject look right? Are the details there? Does it match the text description? This whole process is formalized in equations 2 and 3 in their paper, giving a score based on the VLM's assessment.
That sounds like a pretty sophisticated way to validate synthetic data. Now, when they generate the multi-subject data, how do they do that rigorously and avoid just, trivially copy-pasting things?
Yeah, this is a really crucial part of their method. When making multi-subject data, they start with the single subject model, the S2I model from stage 1, and an open vocabulary object detector, or OVD.
Okay.
They generate an image with one subject, then use the OVD to spot potential other subjects in that image. But here's the key. Instead of just cutting out that detected object to use as the second reference image,
They don't just crop it.
no. They use their trained S2I model, again, to synthesize a completely new reference image of that second subject they identified.
Huh. Why go through that extra step of regenerating the reference image? What's the academic thinking there?
The academic reason is to avoid those nasty copy-paste artifacts you often see, where things look stuck on, and also the lack of real understanding that comes from just cropping. By generating a fresh reference image of the second subject, they give the model a cleaner, more independent visual target.
Oh, okay.
This pushes the model to really understand the text prompt in relation to both subjects and to generate an image where they're properly integrated into the scene, not just sitting next to each other awkwardly. It shows a deeper level of semantic grounding and composition.
Okay, so the architecture and the data framework are definitely innovative. What did the actual experiments show? Did they manage to validate this approach academically against the state of the art?
Yeah, the experimental validation looks pretty strong. They did comprehensive tests using standard benchmarks like DreamBench for single subject stuff. And they also put together their own custom multi-subject benchmark to really push the models in those more complex scenarios.
And the numbers. Did UNO actually score better than existing methods in a significant way?
Yes, the quantitative results are quite compelling. On DreamBench, UNO hit state-of-the-art results. It got the highest Dyno score, 0.760, and the highest ClipEye score, 0.835.
And just remind us, what do those scores mean?
Right, so academically, these are widely accepted metrics. Dyno generally measures subject similarity, how much the generated subject looks like the reference. And ClipEye measures how well the generated image aligns with the text prompt. So getting top scores there indicates UNO is really good at making images that are both faithful to the subject and follow the text instructions.
Okay, and what about the trickier multi-subject task? Did you know hold up there?
It did. For multi-subject generation, again showed state-of-the-art performance, getting the top dyno score and clip-by score, 0.733.
So it handles complexity well too.
Seems like it. These results really highlight Uniview's ability to manage these more complex compositional tasks with multiple subjects while still keeping that high subject fidelity and text alignment. And beyond the numbers, their qualitative results, the actual images shown in figures 6 and 7, they back this up visually. You can see preserving details, editing attributes while keeping the subject looking right, and handling tricky multi-subject scenes pretty effectively.
Did they do any user studies? Sometimes the numbers look good, but humans perceive it differently.
They did. They included a user study with human evaluators, which adds valuable subjective validation. The results consistently showed that people strongly preferred the images generated by across different criteria like subject similarity, text-image match, overall composition, and just general visual quality.
Okay, that helps.
Yeah, it reinforces the quantitative stuff and underlines that the improvements makes are actually noticeable and meaningful.
And academically, to really prove why it works, those ablation studies are crucial, right? Where they take pieces out to see what breaks. What did those show?
Absolutely, ablation studies are key for that. They rigorously tested the contribution of each main component. They found that taking out the synthetic data curation framework, especially if they just resorted to simple cropping instead of generating those new reference images, led to a really significant drop in performance.
Uh-huh.
So that empirically validates how important their sophisticated data generation strategy is for avoiding copy-paste problems and getting genuine multi-subject understanding.
Makes sense. What about the progressive alignment and the UNOP thing?
Yeah, taking out the progressive cross-modal alignment also caused a noticeable performance dip. That confirms the benefit of their staged training for stabilizing learning and integrating all the information better. And maybe most notably, removing UNOP resulted in a substantial drop in the subject similarity scores.
So UNOP really does help with keeping the subject looking right.
Exactly. It directly shows how effective UNOP is at tackling that attribute confusion problem and improving the model's ability to represent the subjects accurately. They also compared UNOP against simpler ways of offsetting positions, shown in tables 5 and 6, and UNOP came out on top, showing its specific design was superior.
Okay, so the experiments, the numbers, the user study, the ablations, it sounds like there's strong academic backing for the UNO framework and its components being both novel and effective. So zooming out, what are the broader academic implications here? And maybe potential future research directions coming out of this?
Well, the academic implications are pretty significant, I think. This whole model data coevolution idea offers a really promising way around the data limitations that have kind of held back customized image generation for a while.
A new paradigm, potentially.
Could be. Act as a strong proof of concept, showing you can have a single unified architecture that handles both single and multi-subject generation well, without needing that expensive per-subject fine-tuning.
And the high-quality synthetic data they made, could that be useful for other researchers too, beyond just training UNO?
Oh, definitely. That rich, carefully filtered synthetic data set is a valuable resource in itself for the wider AI image generation community. People could use it to train or evaluate other models, maybe push things forward in related areas.
And future work.
Looking ahead, the authors suggest expanding their synthetic data pipeline to cover more tasks, like detailed editing, styles, maybe more complex scene arrangements. This could open doors for research into making generative models even more versatile and controllable down the line.
Of course, no research is perfect. What limitations did the authors themselves point out from an academic angle?
Right, they do acknowledge that their current synthetic data framework mostly focuses on this subject-driven generation task. It has, let's say, relatively limited data specifically for things like really intricate image editing or applying lots of different artistic styles.
So it's focused.
It's focused. So while generalizes well within its trained domains, subject-driven generation, its performance might be comparatively less strong on tasks that need a lot of specialized training data for, say, editing or stylization that wasn't really in its training mix.
Okay, that makes sense. So to kind of wrap up the key academic takeaways for our listener, we've got this really innovative concept of model data coevolution, this clever progressive cross-modal alignment training, and the nifty UNOP mechanism. And all these work together for significantly better control and quality in subject-driven image generation, especially when things get complex with multiple subjects.
Precisely. You summarized it well. Really feels like a significant step forward in that academic quest for highly controllable, scalable image generation. By smartly using synthetic data and introducing these novel architectural tweaks, it definitely pushes the boundaries of what's currently possible in the field.
It really makes you think, doesn't it, about this evolving dance between AI models and the data they learn from? I mean, if systems can start strategically generating their own high-quality training data, how might that fundamentally change the game for AI and machine learning research, even beyond images?
Yeah, what other areas could that apply to?
Exactly. What new theoretical ideas or practical hurdles might pop up from this kind of self-evolving AI? It's certainly a fascinating space to watch. And for those listening who want to really get into the technical weeds, we definitely encourage you to check out the project page and the code repository. We'll put the links in the show notes.